Hey guys, my name's Denise and I'm the first ever math Scot, so I thought I'd help you poor unfortunate souls do some math today. First, let's put on our math hats. Am I the only one that has one? So we're going to be doing 9.7 Taylor polynomials and approximations, and we're going to specifically I learned some English, work on the remainder of a Taylor polynomial. So let's get started because I don't know how to talk, so we're just going to try to math. So this is just the definition straight from the textbook, so I'm just going to read it out loud and you can follow along, and then I'll break it down for you. So, to measure the accuracy of approximating a function value f of x by the Taylor polynomial Pn of x, you can use the concept of a remainder, Rn of x, defined as follows. F of x equals Pn of x plus Rn of x. Now, f of x is the exact value, Pn of x, the approximate value, which is what you find, and remainder is what we're going to learn how to find today. Rn of x, your remainder, will be the gap, basically. The gap between your approximate value and your exact value. So how off what you find is. Moving on. So Rn of x equals f of x minus Pn of x. That's just this right here rewritten. The absolute value of Rn of x is called the error associated with the approximation. That is, error equals the absolute value of Rn of x excuse me, equals the absolute value of f of x minus Pn of x. The remainder is just what's left over, as I said before, between your exact value and the approximate value that you find. The error is that, but in the form of an interval. Okay, so now we're going to talk about Taylor's theorem, which is the theorem that allows us to find the remainder and figure out how accurate our approximation is. So, if a function f is differentiable through order n plus 1 in an interval I containing c, then for each x in I there exists c between x and c such that f of x equals f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared. That continues on. And then you move on to f to the nth prime of c over n factorial times x minus c to the nth power plus Rn of x, where Rn of x equals f to the n plus 1 prime of z over n plus 1 factorial times x minus c to the n plus 1 power. Now, this is your n plus 1 derivative here, so the following derivative from this one, of z. Now, z is a new variable. I know, it's scary. Too many letters. Anyways, so we'll find out what this z is, but it is different from all of the other values that we've seen so far. But the same formatting is seen here and here and here as in the remainder. It's just that new variable. That's the only real difference. So over n plus 1 factorial, same thing, times x minus c, same as all the others, to the n plus 1 factorial. These values always match, and if they don't, then you did something wrong. Now, that's not saying that it's always going to look like they match, because these are actual values. So it could cancel out with the denominator, or it could reduce the denominator, so it might not look like they're the same. But if you were to actually write it in this form, then you'll see that it will always be the same. And then you can reduce it, simplify, whatever you want. Now, before I get into any examples, I just want to make this cool little connection for you guys. Speaking of connections, like my nails? Anyways, so What this is saying is that the absolute value of Rn of x is less than or equal to x minus c to the n plus 1 power over n plus 1 factorial times max absolute value of f n plus 1 prime of z, where max absolute value f n plus 1 prime of z is the maximum value of f n plus 1 prime of z between x and c. So this is just the absolute value of your remainder. It's either going to be equal to this side or it's going to be less than this. So x minus c is the same thing we've been seeing for the Taylor polynomial for the remainder function. It's the same concept. X is just a variable. It's whatever is where you would plug in whatever value you're trying to approximate. Minus c, c is your center, n plus 1 over n plus 1 factorial, times max absolute value f n plus 1 prime of z. What this means is that z, this crazy new variable that we're seeing, is going to fall between the values of x, the value you're trying to approximate, and c, your center. So that means it could either be equal to x or equal to c, or it could fall somewhere in between the two. So now I'm going to show you this case that might look a little familiar, or I hope it does. So Taylor's theorem states that when n equals 0, f of x equals f of c plus f prime of z times x minus c. Here we're just rewriting this line. Now, one more step. You're just dividing both sides by x minus c. So it moves it to this side. So it's f of x minus f of c over x minus c equals f prime of z. Now, does this look familiar? I know it probably looks familiar, but can you identify what it is? I'll give you a second there to try to figure it out.
The mean value theorem.
Your favorite, I know. Before getting into any examples of our new topic, I'm just going to review approximations real quick, just to refresh it in your mind. The problem that I chose was approximate the function at the given value of x. The function they give you is e to the 3x. I picked this because it's an e to the x function, and that's my favorite function because every derivative of e to the x is just e to the x, and that's pretty cool if you ask me. Sorry, I like math. So the value of x that you're trying to approximate is 1/2, and they give you the value of n. In this case, n equals 4, so that just means that you're going to find the 4th degree Taylor polynomial. And in this case, it's actually a Maclaurin polynomial because it's centered at 0. So I'm just going to begin by just going to rewrite the function. And I'm hoping by this time you can derive. So I'm just going to find the first 4 derivatives of this function. And you do the same. I know, that was amazing. I'm super deriving. So now we're just going to plug in our c. In this case, c is 0, so e to the 0 is just 1.
Over here, it's just 3 times 1, so 3. 9 times 1, 9. 27 times 1, 27. And 81 times 1, so 81.
So now we're just going to use these values to build our Taylor polynomial. So this is 4th degree. So f of c plus f prime of c over 1 factorial. I'll write it for you guys this time. Now this would normally be x minus c, but since our c is just 0, we don't really need to write that, so you can just write the x. And this is to the 1st power. I'll write that for you guys too. Now you just continue plugging everything in and building up your polynomial. Now you're trying to approximate 1/2, f of 1/2, so we're just going to plug that in now. Now you would just plug this in to your calculator to find its value. I already did that just to save time. And you end up getting 4.3984. Now, just for you guys to see how accurate that is, you don't really need to do this for the problem because it doesn't ask for it, but just to show you guys. I just plugged in e to the 3/2 power into my calculator just to see how accurate or how close to our approximation it is. So, sorry. E to the 3/2 because it's e to the 3x and you're approximating at 1/2 equals 4.481, one more place value, 7. So it's not exact, but it's pretty close. And if you were to go to a higher degree Taylor polynomial, this number right here would be much closer to this one. But that's still pretty accurate. So now we're gonna see just how accurate it is. Okay, so now we're gonna determine the accuracy of our approximation. I rewrote some of the key parts of what we just did for our approximation, and this is the information we're gonna use in order to find the remainder and determine the accuracy. Okay, so I wrote the original function, evaluated it at our x, which was 1/2, so it's e to the 3/2. This was the Taylor polynomial that we found and its value at our x. So this was our approximation. Now for our remainder, we're going to, let me just write out what our remainder would be. We used a 4th degree polynomial, so this is going to be a 4th degree remainder of x. So this is going to equal, since this was a 4th degree, this is going to be a 5th. Sorry, my marker's not working too great right now. Of z over 5 factorial times x to the 5th. So I went ahead and found the 5th derivative already for this function right here. And this is what we get. So I'm just going to rewrite it right here. Sorry. R of x equals 243 e to the 3z, because this is our variable right here, over 5 factorial times x to the 5th. Now we are going to find what our z is, or what we're going to use for z. I'm just going to take out this section right here because this is just a number, and x we are just plugging in our 1/2. So I'm just going to rewrite this down here. Now, from a previous definition that I gave, we found out that the value of z is going to fall somewhere in between our c and our x. Our x here is 1/2, and since this is a Maclaurin, our c is 0. So the value of the z is going to be somewhere in this interval. So in this case, this part right here, which is going to determine how big this entire term is, because it's the only thing that is an interval, so it has the possibility of changing. We have to figure out what z we can use here to make this the greatest possible value. So what you're going to do is check the endpoints. And we see that at 0, this would just be e to the 0, so 1, 243 times 1, so it would just be 243. So in this case, this number right here would be the z that we would use to make this the greatest possible value. Now, right now, it just so happens that our z is going to be the same as our x. That's not always the case. Sometimes it can be the same as our c. And in theory, z can be anywhere in this interval, but we're just trying to determine the greatest possible error. So if anything, it's just going to be more accurate than what we found. So we're going to use 1/2 for z, so I'm just going to erase it so we have more room to work with. And I erased too much, but that's okay. So I'm just going to rewrite the remainder. And I'm just going to plug in 1/2 just so we have that value now. So I'll just rewrite it, 243e to the 3/2 now, over 5 factorial times x to the 5th. And this is going to equal 0.2836. So that is our remainder. Up here, we have our approximation. So now we're just going to plug in things to find the bounds of our error. What it's basically going to look like is going to be our approximation. Is that in frame? Yes, okay. The actual is less than or equal to our approximation plus our remainder. So now we're just plugging in things. This right here comes from the definition that we used earlier about the absolute value of the remainder. So just look back to that if you want to figure out where this comes from, but just in order to save time, I'm just not going to do that right now. So now we're just plugging in things. Our approximation we have up here. So this is 4.3984 less than or equal to our actual value is what we're trying to approximate. So it's this. So it's e to the 3/2 less than or equal to our approximation plus our remainder. So it's this value, this right here, 4.3984 plus this remainder, so plus 0.2836. It's an 0 point that. So now I'm just going to rewrite this. And add these two up, and you will get 4.6820. So this basically means that the actual value of this, the real value that you would get if you were to just plug this into a calculator, falls somewhere within this interval. This is your approximation, so it could either be exactly your approximation or greater than, but the maximum difference between the actual value and your approximation is this right here. So this is the maximum amount that your approximation can be different from the actual value of this. From when we did it before that I showed you that I plugged this into the calculator and we have an answer, we got that the value of e to the 3/2, the actual value is 4.4817, and that in fact does fall into this interval, so it's another way to check that we're correct. So for any value that you plug in for z that is in between our c and our x being 1/2 and our c being 0, any value that you plug in will give you nothing greater than this. So this is the maximum value that you can get, which means that no matter what you plug in, you will be at most this far away from the actual value, which is not that bad, but it's also not the greatest approximation. So if you were to do a higher degree, you would get a more accurate value, and we'll see that with different functions. Okay, so now we're going to be moving on to approximating a value to a desired accuracy. I'm going to be doing the example from the textbook, but I'm just going to walk you through this one because I know the first time I saw it, I did not understand it, and it took a really long time. Lots of videos and asking questions to figure out what exactly happened because they don't give too many details. And ain't nobody got time for that. So I'm going to help you out. So the question was, determine the degree of the Taylor polynomial Pn of x expanded about c equals 1 that should be used to approximate ln of 1.2 so that the error is less than 0.001. So we're just going to get started, and what we're going to do first is we're going to start off by basically just writing down the information that we have and that we don't have, just so we know what we need to find and what we have to work with. So we're going to start n. We do not know what our n is. That's what we're trying to find. That's the degree of the polynomial. Our x is 1.2. Our c is 1. That's our center. And the function right here, f of x equals ln of x. Oh, and they also give us our remainder. So the remainder is going to be 0.001. It's actually going to be less than this, but that's the remainder they give us. So I'm going to start with the remainder formula. So I'm just going to write it out, just so you can see what we do when we start plugging in things. In this case, we actually have a z that is not 0, so it is important that you write that. Now we're just going to plug in the values that we have. We don't have a z, because that's what we need to find right now for the remainder, and we're trying to find the n for the problem. So we have an x and a z. So we're just going to rewrite everything else, because we don't have it yet. N plus 1 factorial. And our x is 1.2, our c is 1. Just going to rewrite that one more time, just to simplify it. So this is going to be 0.2 to the n plus 1. Now, this right here, we're not given it in the problem, but we should know it, or we could find it. The n plus 1 derivative of ln of x. So that's just going to be, and we'll just do it of x right now. That's going to be negative 1 to the n times n factorial over x to the n plus 1. Now plugging that, we're just going to plug this into right here, and we're just going to rewrite it so it's all one fraction, just to make it easier to see. I'm just going to move this over here. So it's going to be negative 1 n times n factorial times 0.2 to the n plus 1 over, we're going to keep this n plus 1 factorial times this, our variable is z, not x, so it's just going to be z to the n plus 1. Now we see that we can reduce this. This would cancel out and you would be left with an n plus 1 in the denominator. This should be an absolute value, so that will get rid of this negative 1 right here, so that's gone. So we're just going to write what we have left. So 0.2 to the n plus 1 over, this is just n plus 1 now. It's not a factorial because it canceled with this right here, times z to the n plus 1 power. Now we need to find what our z is. From the previous example, we saw that our z is going to lie somewhere in an interval between x and c. So our z is going to be somewhere in this range. So what we're going to do now is test our endpoints to see where this right here would have the greatest possible value. Sorry guys, you couldn't see any of that. I'm just going to move it up. Okay. So we need to test the endpoints to see where this fraction right here will have the greatest possible value. So plugging in 1.2, this would have a very large denominator, and we don't want that right now because we are trying to find the greatest possible value. Plugging in 1 would just be simply 1, and that'll be a much smaller denominator than if we were to plug in this, which making the fraction bigger. So we're going to use 1 as our z. So you see, unlike the last case where our z matched our x, now our z matches our c. So this is just going to be 1. So all we're left with right now is 0.2 n plus 1 over n plus 1. Now, let's see what I can erase. So what we have here is they give us that the remainder should be less than this. So actually, let me just rewrite that here. So we're just gonna set this equal or less than that. So we're gonna have 0.2 n plus 1 over n plus 1 is less than 0.001. Just gonna erase that down here now. Now this is the weird part from the example where it just jumps to a completely rewritten inequality, and it took forever for me to figure out what they did and why they did it. So I'm just gonna show you how they got to the point that they reached and then explain it a little bit. So what we're gonna do is we're going to divide. Well, first we're gonna multiply each side by n plus 1, just so we don't have any more fractions. So it's gonna be 0.2, 0.001 times n plus 1. Then we will divide each side by this value right here. So this will just become 1, and dividing this by that is the same as just multiplying by 1,000. So we're just gonna write it like this. This is equal to 1, so it's just gonna be n plus 1. Now, 0.2 is the decimal version of the fraction 1 over 5. So we're just gonna write it that way. This is more of a recognition sort of thing from their rewritten inequality, where you saw a random 5 and kind of took a little bit to figure out where that came from, but that is where that 5 comes from. It's just 1/5 is equal to 0.2, so that's that. So now we're just gonna split up the fraction. So it's gonna be 1 to the n plus 1 over 5 to the n plus 1. This is simply 1, so you're left with 100, or 1,000, I'm sorry, over 5 to the n plus 1, n plus 1. So now you just multiply 5 to the n plus 1 on both sides, and you're left with 1,000 is less than n plus 1 times 5 to the n plus 1. Now this is what we see in the textbook, and that's how they got to that. Now, as far as why they did that, honestly, it's literally just so you would not need a calculator. Because at this point, all you do is you're plugging in n's straight off the top of your head and just testing the values. So in order to make it easier for you to recognize and to get simpler answers than if you were to be dealing with these decimals up here and the whole fraction situation, they're rewriting it just so it's easier for you to do in your head. So at this point, you're just going to be plugging in values for n. So we're going to start with n equals 1. So you're just plugging in n equals 1 up here. So it's 1 plus 1 is 2. 5 to the 1 plus 1 power, that's just 5 squared. 5 squared is 25, times 2 is 50, so that does not work. So it's not n equals 1. It usually won't be something that small, but just to check. Next, n equals 2, sorry. So 2 plus 1 is 3. 5 to the third power, or 5 cubed, is just 125, times 3 is 375, so that does not work. We're going to go to n equals 3 now. 3 plus 1 is 4. 5 to the fourth power is 625. 625 times 4 is 2,500. So this is the smallest value where this inequality will be true. So our answer for this question is n equals 3. So you would need back to the problem up here, you would need a third degree Taylor polynomial in order to have an error less than 0.001. Well, that's all, guys. Thanks for joining me, and I hope you learned something.